Yeah, so I'll be talking about this work which was published last year in December with the same title. Um, Before going into details, so I'll start with introducing the basics of bipartite entanglement and what I mean by state transformations, and then I'll introduce this notion of catalytic transformation. Um, then I'll talk about this notion called asymptotic transformations, which is state transformations when you have many copies. And then I'll talk about catalytic asymptotic equivalence, which is the central part of the title. And why do we use this? So once we prove this catalytic asymptotic equivalence, we can actually solve this question where the target is pure, and then you have a noisy state, and you want to get to a pure target state using such catalytic transformations. So yeah, let's start from basics. So the setting we consider is as follows. So we have two parties, Alice and Bob, and they have a classical channel, so they can share the experimental outcomes with each other. And they also share a bipartite entangled state, rho AB between them. So this is the setting we stick to. And because Alice and Bob are spatially separated, they can only perform quantum operations in their own laboratories. And this setting is called local operations and classical communication. So in order to better understand what this LOCC looks like, so let us start by understanding a simpler version of LOCC. It's called one-way LOCC. And what is it is follows. So what Alice does is, so Alice performs a quantum measurement locally in her laboratory. And since she does a measurement, she gets outcomes, which are denoted by I. So she does a measurement, she gets an outcome. And Alice then communicates this outcome to Bob. So she calls Bob on telephone, and then she communicates the outcome she gets. And what Bob does is, Bob does a local deterministic quantum operation dependent on the condition of Alice, depending on the outcome of Alice. So Alice performs a measurement, and based on the measurement outcome, Bob performs a deterministic quantum operation on his laboratory. And this is called one-way LOCC. So it's called one-way LOCC because the communication is from Alice to Bob. So this is how it looks like. So a one-way LOCC map mathematically can be expressed as follows. So Alice performs a quantum measurement, and these MIs are completely positive trace non-increasing maps. So quantum measurement and quantum information theory is a completely positive trace non-increasing map. And once she gets an outcome I, based on the outcome I, Bob does a CPTP map, which is Ni. And Ni here is a deterministic quantum channel. And then you average all the outcomes of I. And this gives the one-way LOCC channel.
And overall MI, over IMI is trace.
Yes. So if you summation over I, MI is trace preserving. But each of MI is completely positive but trace non-increasing. But NIs are completely positive trace preserving. They are deterministic. Right? And this is how a one-way LOCC channel. And a general LOCC channel is actually a concatenation of finite number of one-way LOCC channels. So you take a one-way LOCC channel from Alice to Bob, and then another one-way LOCC channel from Bob to Alice, and then you do series one after the other. And then every general LOCC map can be written like this. So this sort of a simpler way to understand LOCC. Okay. So let us introduce this definition of separable states. So separable states are bipartite states between Alice and Bob, such that they can be written as convex combination of such product states. So sigma I tensor tau I is a product state, and you take convex combination of those, and such states are called separable states. The thing is, the key fact is LOCC operations cannot generate entanglement out of separable states. What it means is as follows. So you take a separable state rho, you apply a LOCC channel, you'll get back a separable state. That means if you start with a separable state, by doing LOCC channels, you'll end up in a set of separable states. You'll not get any state which is out of the set of separable states. And the states which are out of the set of separable states are called entangled states. So these are the basic definitions we need. Now I'll talk about state transformations. So what do I mean by state transformations? So let's say Alice and Bob share an entangled state rho AB, but they want to have some other entangled state sigma AB. The question is, can they go from rho AB to sigma AB by doing LOCC? Right? That's the question. So if you allow for all quantum operations, then of course you can go from rho AB to sigma AB.
But there's one question over here that
Yeah.
whether LOCC channels act as a operation for absolute available plus.
Yes. No. Because by doing LOCC, you can get to a pure separable state, and pure separable state is not absolute. So if we allow for all quantum operations, then of course you can go from rho AB to sigma AB. But now we can't, right? We have a restriction. You can only do LOCC. Now the question is, can you do LOCC and go from rho AB to sigma AB? And this is essentially the question of state transformation. For pure states, this question has been solved in 1999 by Nielsen. So if I give you a pure bipartite state and you want to know if you can go to another pure bipartite state phi, then through LOCC, it's possible if and only if the following conditions hold. I'll explain what these conditions are. So what you do is you take your pure state psi AB and find out all the Schmidt coefficients, right? And similarly, find out the Schmidt coefficients of your target state phi AB. And if the Schmidt coefficients of psi majorize the Schmidt coefficients of phi, then there's a transformation, LOCC transformation taking you from psi to phi. The thing is, it's a necessary and sufficient condition. If this majorization condition doesn't hold, then there doesn't exist transformation. And what are these majorization conditions? So what you do is you take the Schmidt coefficients of psi, arrange them in decreasing order. So Schmidt coefficients, as you know, form a probability distribution. So you arrange the Schmidt coefficients of psi in a decreasing order, you arrange the Schmidt coefficients of phi in a decreasing order, and you check does the largest Schmidt coefficient of phi is greater than or equal to the largest Schmidt coefficient of psi or not. That some of the two largest Schmidt coefficients of phi are greater than some of the two largest Schmidt coefficients of psi or not. And you check the series of these constraints. If all these constraints hold, then we know that you can construct an LOCC channel which takes you from psi to phi. If at least one of these constraints doesn't hold, then there doesn't exist any LOCC channel transforming you from psi to phi. So in that sense, the problem of state transformations when the initial and target states are pure is solved. Now the interesting thing is, take these two states. So consider psi to be this given in equation 5, and consider phi to be this state given in equation 6. What you will notice is neither psi can be transformed through LOCC to phi, neither not phi can be transformed through LOCC to psi. Because you can, since you know the Schmidt coefficients, you can check this majorization conditions which were in the previous slide, and one can easily check that neither of these two transformations are possible. So in some sense, psi and phi are completely independent. You cannot transform one into each other. But surprisingly, let's say Alice and Bob have an additional state eta along with psi. Then psi tensor eta can be transformed to phi tensor eta. So you can calculate the Schmidt coefficients of psi tensor eta, which are essentially product of the Schmidt coefficients, and you can also calculate the Schmidt coefficients of phi tensor eta, which are product of the Schmidt coefficients, and then one can see that such transformation happens. So what's happening now is you have this eta, which is not consumed in the process. You'll get back after the transformation, but it is implementing the transformation which is not possible otherwise, right?
So in the majorization level, so why does it happen when you add an ancillary system over here?
You do the same majorization, but you just the Schmidt coefficients of psi tensor. Now you need to consider the Schmidt coefficients of psi tensor eta. Exactly. And the Schmidt coefficients of psi tensor eta are essentially Schmidt coefficients of psi times Schmidt coefficients of eta, right? And once you do that, you will see this is possible. So the crux is this additional entangled state eta. It enables a transformation which would not be possible otherwise, and it also remains unchanged in the process. And this is the idea of catalysis. So this was first introduced by Yonaker and Plenio in 1999, and catalysis is a resource which is not is unchanged during the protocol, but without which this transformation wouldn't be possible. All right. Now the question is, can you completely characterize such catalytic transformations? What do I mean by that? So if I give you two pure states, psi and phi, can you say when does a catalytic transformation exist between psi and phi or not? And this thing has been solved. So if I give you a pure state psi, and if I give you a pure state phi, I ask a question: can you do LOCC using catalyst? And can you transform psi to phi or not? And this can be the solution of this looks like this. So you calculate the Schmidt coefficients of psi, and U is it's a uniform distribution of just ones. and you calculate the Renyi entropies, the relative Renyi entropies, and check if all the relative Renyi entropies of, so they are sort of infinite conditions. So there are Renyi entropies from half to infinity. It's a continuous family of functions, and then you check if all these inequalities hold or not. Here, U is a uniform distribution. Lambda is the Schmidt coefficients of psi, and lambda, this one is the Schmidt coefficients of phi. Well, so the key point is there are these infinite set of conditions which one need to check to know if there exists a catalytic transformation from psi to phi or not.
When you say that catalytic transformation psi to phi,
yeah,
that is only on the assumption that LOCC you are talking.
Yes. You're doing LOCC and you allow for additional pure states which should not be consumed during the protocol.
So if I consider the interset of free operations,
interset of what?
The free operations.
Yes.
Can you is the LOCC the exhaustive set of free operations?
No.
So in that context, it will change. No, if
yes, this conditions might change. Yeah. But these conditions are only for LOCC. So if you allow for LOCC and you allow for additionally some entangled pure states which you can use as catalysts, then the transformation is possible if and only if such infinite set of conditions hold.
Is there any intuition for it? Does that state eta, does that necessarily need to be maximally entangled?
No. It doesn't. So it has to be tailor-made for the transformation. So this is an existence theorem. Yeah. If this conditions hold, then there exists an eta. Yeah, it can be a very complicated, finely tuned pure state for depending on psi and phi.
I think often it is not maximally entangled.
Yeah, often it's not maximally entangled.
Okay.
So the problem with this is, firstly, as you see, the conditions are not easy to check. If I give you two arbitrary pure states and you want to check if a catalytic transformation exists between psi to phi, you need to check this infinite number of conditions. It's not possible.
Yeah. So can I also think about this in terms of like distillable entanglement and entanglement costs?
No, because these functions which you see are this relative Renyi entropies are not exactly, are neither distillable entanglement nor the cost.
Okay, but okay, so can you put the reactance condition?
Yes.
So is there an equivalence between that and like distillable entanglement or cost? But is that independent as well?
You mean give me a second. Yeah, which one you say?
Yeah, this one.
Yeah.
So I'm asking if we can go from psi to phi only if like
So-
entanglement cost of phi is lesser than distillable entanglement of psi.
Yes. So distillable entanglement of psi has to be greater than distillable entanglement of phi is a necessary condition.
No, but sorry, I was saying distillable entanglement of psi is lesser than entanglement cost of phi.
So the first thing, because they are pure states, distillable entanglement and entanglement cost are the same.
Okay,
Right?
Right.
So distillable entanglement of psi being more than distillable entanglement of phi,
That is not necessary.
it follows from these conditions.
Okay. But is that also a sufficiency condition?
No.
Okay.
Less than sufficient conditions are given by these.
Okay.
So if you take these conditions, then the distillable entanglement of this being greater than distillable entanglement of this follows. Because distillable entanglement of this is essentially the entropy of the this area. It follows from this.
Majorization condition.
Yeah, these are the majorization. Yeah, I'm just presenting these here. So yeah,
These are entropy, right?
yes. So if you
Related with
alpha equal to 1 here.
and
Yeah.
related because it's and in the previously this majorization the numbers that you had. The
Yeah.
vector.
Yeah.
Yeah,
It's essentially entropy of this vector.
Yes.
Yeah. So the distillable entanglement means the entropy of this vector split coefficient.
Okay.
Yes. And yeah, it follows from these conditions. And also, for example, if you take alpha equal to half, you get something like distillable entanglement because it's alpha equal to half is essentially relative entropy, which is entropy minus log B. Exactly. So distillable entanglement of psi being greater than distillable entanglement of phi also follows from these conditions. So catalytic conditions are more than that. They're more stronger here. Because catalysis is, at least this notion is more stricter. So the firstly, these conditions are not easy to check, right? Because the infinite conditions one have to check. And secondly, if you see the previous slide, the catalyst is pure. It's a pure state. And even in this analysis, they only study pure catalyst. They only allow for pure catalyst. They don't allow for catalysts which can be mixed states. So this is open. So we don't know if you can do better by allowing for catalysts which are mixed. So this is so these two are sort of backdraws of this drawbacks of this analysis. Yeah. And so this is where we try to overcome this. So firstly, our motivation is to somehow allow for mixed catalysts and come up with a condition which is simpler than these, because these are very hard to check. So that's why we introduce something called correlated catalysis, which is as follows. So whenever I write S, it means Alice and Bob. So Alice and Bob I write as a system. So now I want to go from rho to sigma by using catalysis and LOCC, of course. So now I'll define what do I mean by catalysis from now. So I can go from rho to sigma if and only if, yeah, you allow for a catalyst tau and you do a LOCC such that you end up in some state of system and catalyst mu SC, such that if you trace out the system, the catalyst should be exactly same. This is the idea of catalyst, that catalyst should not change. So mu C should be catalyst, but mu S should be close to the target state which you want to achieve. So the trace distance between mu S and sigma S should be less than epsilon. And the epsilon can be made arbitrarily small by choosing suitable LOCC map and suitable catalyst. And if this is possible, then I say you can transform rho to sigma using catalysis.
So epsilon is both dependent on the map and the
Yes. The promise is that you can make epsilon arbitrarily small by choosing a suitable catalyst and a suitable LOCC map. Is there any question with the definition? Okay. So once we have this definition, I'll also introduce a well-known definition of asymptotic transformations. What do I mean by asymptotic transformations? So asymptotic transformations are many copy transformations. So until now, we just had one copy of rho and we want to transform into one copy of sigma. But asymptotic transformations, what we do is we talk about something called the rate. So we say that an asymptotic transformation from rho to sigma is possible with rate R if you can take n copies of rho and then you apply LOCC map and then you get a mu which is on M systems now, such that this mu is close to m copies of sigma, because sigma is a target state. It has to be epsilon close to m copies of sigma, and ideally we want to achieve it with rate n, right? So the m should be n times r, but it might not be the same. It can be slightly small. So n times r minus m there can be a slight deficit, but the deficit when you divide it by n should be less than delta, and such that epsilon and delta again can be made arbitrarily small by choosing a big enough n. If such r is possible, then we call it as rate, and the supremum of all these rates is called asymptotic transformation rate. It's a bit of loaded definition, but what essentially we want to do is we want to take n copies of rho and we want to achieve n times r copies of sigma, right? But we allow for certain, so we sort of make it slightly weaker. We don't want to achieve exactly sigma, but we allow for some mu such that mu is close to m copies of sigma. So there can be a slight error. And we don't want exactly n times r copies, but we allow for a less number of copies is also fine. And we call this as a deficit, with the promise that the error and deficit can be made arbitrarily small if you can choose by choosing bigger and bigger n. And yeah.
N and R, this means you want to target N and N into R copies, right?
So we start with n copies of rho, and we want to get n times r copies of sigma.
Exactly. And you get n copies.
Yes, which is slightly smaller than n times r. So there's a deficit in number of copies.
But does the deficit in the number of copies dependent on the state mu that you are getting?
Yes, because mu is essentially is on m systems, right? And m is less than n times r. So mu is a state on m systems, and m
is less than or greater than, because we are between
less than, right? Yeah, n times r can be more than m, so there can be slightly deficit in the number of copies you get, but the deficit can be made arbitrarily small by choosing larger and larger n.
Won't r be something that you choose?
Yes, so r is something you choose.
So if that is the case, then if you can choose an r,
yes,
As that deficit is minimum.
Yes.
And you do that.
Yes, exactly. So whatever possible R such that this deficit can be made arbitrarily small to zero is called the achievable rate. Achievable rate. And asymptotic rate is optimal rate. So we call asymptotic rates as the supremum of all the achievable rates. So if you can fix R to be 2 and you can do this, then it's an achievable rate. And you take the supremum of all the achievable rates and then you define it as the asymptotic rate. It's like the largest rate which you can do this transformation. So essentially what you're doing is you're transforming n copies of sigma to n times r copies of, so n copies of sigma to n times r copies of sigma, sorry, n copies of rho to n times r copies of sigma, but you're not doing it exactly. There's some error and then deficit, but both of them can be suppressed by choosing bigger and bigger n.
R is like less than 1.
Well, r can be greater than 1 too.
Okay.
R can be any number, yeah. Yeah, you can also have, yeah, R can be real number which is greater than 0.
What is the superscript S1 to S10?
So these are the number of systems on which mu is the state. You use the state on this m number of systems, right? And so essentially mu is almost sigma tensor m. So mu is almost sigma tensor m, yeah. But this is slight error. And m is not exactly n tensor, but this is also slight deficit. Yeah. And typically this is how distillable entanglement costs are also defined. You allow for some error and some deficit, with the promise that both these things can be suppressed with arbitrary small. All right. So this is where distillable entanglement comes from. Distillable entanglement is essentially the asymptotic rate, the same definition, but when the target state is 5 plus, 2-qubit maximal entanglement state. So if you fix the target, the sigma to be 5 plus, then you get something called a distillable entanglement, the optimal achievable rate. And one more definition, this is sort of a classic definition which was used in this old papers, which we say that rho is reducible to sigma if the asymptotic rate of transforming rho to sigma is at least 1. Right? It can be less than 1, it can be more than 1, but if it's at least 1, we call rho is reducible to sigma. This is the definition, yeah. So since we introduced distillable entanglement, I'll introduce some properties and some nice properties which are later which will be used later for some proofs. The first, distillable entanglement, if you take a separable state, is 0. Right? You cannot distill singlets with any rate if you start from separable states. Secondly, distillable entanglement is additive. So if you take n copies, the distillable entanglement is actually n times distillable entanglement of each of the copies. And the third thing is distillable entanglement cannot increase under LOCC. So if you take a state rho and you apply LOCC on it, the resulting state will have distillable entanglement at least not more than the initial state. This is called monotonicity. The fourth one is an important property. It's called superadditivity, which essentially is, let's say you have a state which is on two systems, system 1 and system 2. So system 1, you can look at it as Alice 1, Bob 1, and system 2 is Alice 2, Bob 2. So distillable entanglement is at least the distillable entanglement of the first system plus the distillable entanglement of the second system. This is called superadditivity, and the way to look at it is as follows. If you have a state which is acting on two systems, you can distill singlets from the first one and the second one independently. If you distill independently, then you will get essentially number of singlets which is given by this side, the right hand side. But you can come up with more clever protocols and do not independently but some adaptive methods, and you can probably in principle get more number of singlets. This can be possible, yeah. So that's why distillable entanglement has this nice property of superadditivity. So yeah, we will use them later on. One more definition, which this is probably the last definition I'll introduce. It's called marginal reducibility, which is, in order to define marginal reducibility, we need to define something called a variant of asymptotic transformations called marginal asymptotic transformation. If you look at the previous slide of asymptotic transformation, it's almost similar, but there's a very slight change. So again, we want to transform n copies of rho to n times r copies of sigma, but we get mu. Well, there's an error. But the thing is, if you see, earlier we had such a condition. If you look at the second line, now I'll go to the previous slide. Look at the second line now. The constraint we wanted is mu as a whole should be close to m copies of sigma, right? It has, but now if you see, we change this condition slightly a bit. Each of the systems have to be close to sigma. The other definition is actually the same. This is the only difference between this notion of marginal asymptotics and the notion of the previous one. This is a slightly weaker constraint because As a whole, if mu is close to m copies of sigma, then this follows. But from here, it doesn't go opposite. Yeah. So this is sort of a slightly weaker condition than usual asymptotic transformation. If you have a bulk of a big mu, and just the margins have to be close to sigma, as a whole can be very far from sigma tensor m. So if you allow for such a difference in this error constraint, we have something called this marginal asymptotic transformations. And again, you have the supremum of all these achievable rates as marginal transformation rate. And from definition, so this we again say that rho is marginally reducible to sigma if the marginal rate is at least 1. And from because the error condition here is weaker, the marginal rate is at least the usual asymptotic rate. Well, now I introduced all these things because of the following observation. So earlier when I introduced catalytic transformations, what we had a single copy of rho, we had a catalyst, we do a LOCC and we convert it into a copy of sigma and we get the catalyst back. So catalysis is sort of a single copy phenomenon. But when I talk about asymptotics like marginal reducibility or normal reducibility, it's about transforming n copies of rho to n times r copies of sigma. It's a many copy transformation. But the thing is, these two are somehow connected. And this connection was first discovered by Duan in 2004. So what he noticed was follows. So what he constructed was, so let's say you take n copies of sigma, n copies of rho, right? And you do LOCC, and then you transform it to mu, which is again acting on n systems, right? You take n copies, you do LOCC and transform it into mu. Now, if you can do this, what you can do is you can construct a catalyst tau and a LOCC protocol lambda and go to mu SC, which is a state of system and catalyst, such that if you trace out the catalyst, mu S is essentially average of all these mu's, and the catalyst is exactly preserved. So these mu SIs are essentially this mu S1. For mu S1 is essentially you trace out everything from S2 to Sn and you take the first system. So what you're essentially doing is you take n copies of rho, you're converting it into a big mu, which lies on n systems. If you can do this, what Duan showed is you take one copy of rho and you can get a final state which is essentially average of all these mu's. So this is a single copy catalytic transformation, and this is a multi-copy transformation, and somehow these two are related in this way. You can find the average of all these subsystems. You can get an average of all the subsystems by using a catalyst. And why is it important? This is as follows. So let's assume you take rho tensor n and you get so you take n copies of rho, and let's assume you get m copies of mu. And so what I want to show is the following: if rho is reducible to sigma, so you take rho and you can transform it into sigma by marginal reducibility. That means at least with rate 1. So you take n copies of rho and you can get n copies of sigma using marginal reducibility. Then you can transform from rho to sigma via catalysis. So this is what I'm doing. So this is the first connection between the notion of reducibility, which is asymptotic transformations, and catalysis with a single copy transformation. And this is how it works. So you take n copies of rho, and since it's marginally reducible, you can convert it into mu such that each copy of mu is close to sigma. And then m is of course smaller than n, but the deficit can be it's less than delta. So now you can make the number of systems same by just attaching zeros, and now you have n systems on this side and n systems as beginning. And now you can use Duan's catalyst. Once you use Duan's catalyst, what you can do is you can get from rho to an average of all these subsystems. And since each of the subsystem is close to sigma, the average is also very close to sigma, and the closeness is given by this epsilon plus 2 delta. So what we're essentially doing is, if you can asymptotically transform rho to sigma, then you can also construct a catalyst transforming rho to sigma in a single copy level.
If you can asymptotically transform rho to sigma with rate at least 1.
Yes.
Okay, great.
So the main idea is if you can transform from rho to sigma asymptotically with rate at least 1, then you can construct rho to sigma with a catalyst at a single copy level. Some of these asymptotic transformations and this single copy catalytic transformations are related in this way.
What implies the
Yes. So reducibility implies catalysis. Exactly. So even though they look a bit from two different worlds, one can take this multi-copy transformation and somehow convert it into a single copy catalytic transformation.
other way around?
The other way around was open, and this is essentially the part of main result of this paper. So the equivalence was not complete. There was only one way equivalence. So the known equivalence was reducibility or marginal reducibility implies catalysis was known from Duan's work before. That you can take a multi-copy asymptotic transformation and convert it into a catalytic transformation. So, but what we prove is the following: we actually show the full equivalence. We show that marginal reducibility and correlated catalysis are actually fully equivalent for any pair of distillable states. In fact, it's not only one way, but actually two ways. That means if you can convert rho to sigma with at least rate 1, then you can do a catalytic transformation from rho to sigma, and also vice versa. If you can do a catalytic transformation from rho to sigma, then you can also convert rho to sigma with a rate 1.
But with marginal reducibility.
Yes, the definition of marginal reducibility, exactly. Not with the notion of reducibility. Exactly. And I can quickly go through the proof, but yeah. So I can maybe give a brief sketch of how to prove the opposite. Yeah. So the first part of the proof is done. So marginal reducibility implies correlated catalysis was on the previous slide. Now I try to show correlated catalysis implies marginal reducibility. Right. So this is the definition of correlated catalysis. So if you can transform rho to sigma by catalysis if you can attach a catalyst and do LOCC such that the catalyst is preserved at the end of the transformation, and the system is now very close to the target state sigma with epsilon error. And of course, this epsilon can be made arbitrarily small, right? Now, the key point is we assume that the state rho has to be distillable. So that our proof only works if the initial state is distillable. That means the distillable entanglement is at least 0. So for bound entangled states, our proof doesn't work. So this equivalence we only prove for distillable states. And since the state is distillable, what we can do is actually you can take some copies of state and approximate the catalyst. How do we do this? So what does it mean a state is distillable? That you can take enough copies of a state and get to a Bell state, right? If you can get enough copies of Bell states, then you can get any state you want, and that's what we do. So, and therefore, if you can take enough copies of state and do a suitable LOCC transformation, you can approximate any state you want. So you approximate the catalyst, right? And of course, you cannot get exactly the catalyst because even in the definition of distillable entanglement, you won't exactly get a singlet. You get singlet with an error epsilon, which can be very small, right? Similarly, you approximate the catalyst with an error, let's say epsilon prime, which can be very small. So this is the true catalyst, which was in the definition, but this is the catalyst which we got from taking some copies of rho, which has an error epsilon prime. So now we will use this fact that we can approximate the catalyst. So what we do is the following. So we want to show that rho can be marginally reducible to sigma. So you can transform n copies of rho to n copies of sigma asymptotically. So you start from n copies of sigma, but you divide it into two parts. You take m copies and you take n minus m copies. Now with m copies, you approximate the catalyst. The rest are n minus m copies, right? So first you do LOCC transformation to just transform m copies to the catalyst, of course with a small error epsilon. And now we'll use the catalyst sequentially on each of them to convert each of them to sigma. But there's a slight caveat, but it's not exactly the catalyst, but it's an epsilon approximation of the catalyst. So if it was exactly the catalyst, then of course the sequential procedure would work. But now we have an error. But the thing is, this error can be controlled. That's actually the key observation. So you ideally you need to start with this rho tensor tau. But what we are starting with rho tensor tau epsilon. So there's an error epsilon prime. But note that trace distance can only get smaller and smaller with CPTP maps. So you apply this LOCC on both sides. And this is the final state, the ideal final state which you usually have in definition. But this is the state which we have by having a slightly bad catalyst. But you see the difference between these two is also bounded by epsilon. Well, that essentially means the following, that even though the catalyst is slightly different than the original catalyst, it's an epsilon approximation of the catalyst. by using sequentially, it doesn't go out of this epsilon wall at each step. So you do it once, you see that. So this is the catalyst, right? This and this are upper bounded by epsilon. It essentially means that the catalyst is also upper bounded by epsilon, even after doing the transformation. So the crux of this thing is that even though you have an imperfect catalyst, it's not very bad. It's only epsilon prime bad. But sequentially doing at every step, it only epsilon prime bad. Linearly, it doesn't even grow. The epsilon prime remains constant. That's actually the key point. So by doing this LOCC map, the final state is still epsilon prime. If you trace out again, you'll see that catalyst and the true catalyst are still like an epsilon prime. So the error of the catalyst doesn't grow. It remains constant. And because of this thing, by doing sequentially, each of this state is also very close to sigma, and the error doesn't grow. So you'll actually have an approximation of sigmas and on all these n-m systems. Well, and then you can just throw away the catalyst. But of course, there's a deficit in the number of systems you get. But the deficit is very small because, well, the deficit depends on how many m's you have here, right? And that depends on error. For a given error, you can always choose a large enough n as the deficit is small. So essentially, this is a sketch of the proof. But what we show is this equivalence, yeah, that marginal reducibility and correlated catalysis are the same if the initial state is distillable, if rho is distillable. And how do we use this? So we use this, for example, in the following process. So let's say you have state rho and you want to go to some pure state psi using catalysis. Well, we know from papers before that if distillable entanglement of rho is greater than or equal to distillable entanglement of psi, then rho is reducible to psi. That means you can asymptotically transform rho to psi because the distillable entanglement of rho is greater than distillable entanglement of psi, and entanglement cost of psi is equal to distillable entanglement of psi. And we know that if rho is reducible to psi, then rho is marginally reducible to psi, and rho is that means rho can be catalytically converted to psi. So distillable entanglement of rho being greater than distillable entanglement of psi is a sufficient condition for catalysis. So if this holds, then you can construct a catalyst transforming rho to psi. But is there also a necessary condition? Is it necessary and sufficient? And we can actually use this reducibility. So what we know is, if rho can be converted to psi, if and only if rho is marginally reducible to psi. This is the equivalence. And what is marginal reducibility? You take n copies of rho and you do LOC transformation into mu such that each of mu is close to psi. Right? This is marginal reducibility. Now you use the properties of distillable entanglement. So you apply distillable entanglement here. So we know that distillable entanglement is additive. So this is the first equality. The second inequality follows from the fact that doing LOCC cannot increase distillable entanglement. So if you go from rho to mu, then distillable entanglement can only decrease. Right? This is the second inequality. And then we use this super additivity which I described before. Mu is made up of subsystems, and distillable entanglement of each of the subsystems, you add them, cannot be more than the distillable entanglement of whole. Right? And once you have this, you get this. You take the first and last, and then you divide it by n, and you get distillable entanglement, you get this inequality. But we know that each of this mu is close to, here there's a small slight error. Sigma is essentially psi, the target state. We know that each of this mu is pure state psi, right? Therefore, you can, instead of mu, you can just put psi up to some error epsilon, and then you get this. And this delta and epsilon can be arbitrarily small, so you can essentially make them 0. So what this shows is distillable entanglement of rho being greater than distillable entanglement of psi is also a necessary condition, not just a sufficient condition. And this boils down to the final theorem, which essentially says that if you have a bipartite state rho and you want to go to a bipartite pure state psi, so rho can be converted into psi by a correlated catalysis if and only if the distillable entanglement of rho is greater than or equal to distillable entanglement of phi. So the interesting thing here is, earlier for catalysis you have this infinite number of conditions you need to check, but once you change once you allow for mixed catalysis, that it just essentially boils down to a single constraint. So this constraint essentially gives necessary and sufficient conditions for catalytic transformations. But there's still a small caveat. Distillable entanglement for mixed states is not computable. It's a very hard quantity to compute. But for example, if we take both to be, so one more thing is also addition. So our equivalence only holds if the states are distillable. If the states are not distillable, it doesn't hold. But the other part of the theorem was covered by Ludovico Lamy in this almost the same time. So we had parallel papers in which they solved the other part of the theorem. When the state is not distillable, our equivalent doesn't hold, but there's an alternative proof in that case. So both this result on a whole show that distillable entanglement gives a complete characterization for catalytic transformations. And one good thing is, if a state is pure, then distillable entanglement is easily calculatable. It's essentially the entanglement entropy. So what you do is you take a pure state, you trace out Bob, and you take the entanglement entropy. So you calculate the entropy of the reduced density matrix, and this is H, and this is essentially the distillable entanglement of a pure state. And once you use that, we get back a result which we put a couple of years before, which essentially says that you can transform a pure state psi into some other pure state phi via catalysis, if and only if the entropy of the reduced state of A is greater than or equal to the entropy of the reduced state of phi. And this is interesting because this is somehow entropy always had meaning in many copy limit. So when you have many copies and you want to transform many copies to many copies, that's when entropy arises. But this sort of a single copy characterization of entropy, because it's essentially you want to transform one copy of psi to one copy of phi, and it is completely characterized by the entropy of the reduced system of A. So if the entropy of the reduced system of A is more than phi, then you can construct a catalyst and do it in a single copy level. So to conclude the talk, what I showed is firstly, I introduced catalytic transformations, and also this many copy transformation, and I showed actually these two are equivalent. And then we use this equivalence to characterize catalytic transformations when the target state is pure. And this essentially provides a operational meaning of distillable entanglement in single copy scenarios, because again, distillable entanglement is a quantity which arises when you have many copies, but this is sort of an example where distillable entanglement appears when you have problems where there's only single copy of initial and single copy of the final state. And there's one open problem in this. So let's assume you have an initial state which is pure, and let's say you have a target arbitrary mixed state. We don't know what are the necessary and sufficient conditions to transform. So this is still open. And yeah, so with this I end the talk.